G'day team, welcome back to yet another video. So today we are extending on from that dot product knowledge that we gained in that last video to look at the angle between two vectors. So if we're looking at this little diagram here, we've got a vector v, a vector w, and the angle in between them. Now this red resultant vector here is actually w minus vector v, just translated, so w minus vector v, so this result here, but just translated across. Now remember, this vector w take vector v has the length modulus, or the magnitude of vector w take vector v. So we're going to actually utilize the cosine rule. Now we haven't deep dived into the cosine rule before, sort of to do with vectors. Have a look at my trigonometry videos if you are a bit lost on the cosine rule. They should be uploaded any day now, just to go over that and make sure it's super clear. But for now, take it at face value and understand that c squared, so if I label my triangle like this, A, B, B, so length c squared is equal to the length of a squared plus the length of b squared, take 2 times a times b times the cosine of angle C. So we're going to utilize this, but put this in terms of the vectors that we have in this diagram. So applying this to the diagram, just quickly, we've got vector v is equal to the components v1, v2. Vector w is equal to the components w1, w2. And vector w take vector v is equal to w1 take v1 in the horizontal, and w2 take v2 in the vertical components. Okay, so bear with me, this proof, so we're actually proving our formula today. It does get a little bit messy, so make sure you are following along closely. So c squared is our resultant vector squared, so we need the magnitude of our vector for the length. All right, so we've got the magnitude of w take v squared equals vector v squared plus vector w squared take 2 times the length of v, the length of w, times by cosine theta. Now, hopefully you remember that the magnitude of a vector is the horizontal component squared plus the vertical component squared, square root. So I have substituted that in my equation here. So this here is actually the magnitude of w take v, the magnitude of v, and the magnitude of w, which is more v's, and which isn't what we want. We want w's. Sorry for the ugly w's, but you're going to have to deal with it. Now, I want to leave my magnitudes apart here. I want to leave them like this for now, and you'll see why in a moment. So let me just quickly fix these. These are also w's. All right, so what happens when we square a square root is they cancel each other out. It's like going to the power of 1. So that is exactly all we've done. We've just removed the squares and the square roots from all of these terms. On this left-hand side, we've used our perfect square expansion law. So a squared plus 2ab plus b squared. So I've done that for both terms here. And I've really gone through and just V'd it up. So they're w's as well. So now, if we're looking at both sides of our equation here, all right, if they're positive on both sides, then they'll cancel out if we subtract 1 from either side. So positive w1 squared, I've got a positive w1 squared there, so they cancel out. v1 squared and v1 squared, they cancel out. w2 squared, they cancel out. v2 squared, they also cancel out. So now on this left-hand side, we're left with negative 2 times v1, and then we're also left with negative 2 w2, v2. Now there's a common factor of negative 2 there, so we're going to pull that out the front, and all we're left with is negative 2 times by this w1, v1 plus w2, v2, and on the right-hand side, we're left with that whole second term, negative 2 times the magnitude of v times the magnitude of w times cosine theta. Now the negative 2's cancel out, because if you divide one side by negative 2, you've ended up with negative 2 on negative 2. All right, and then all we've done is put the cosine theta. So we divided both sides by our magnitude of V and magnitude of W. All right, so cosine theta is equal to W1 V1 plus W2 V2 divided by the magnitude of V, magnitude of W. Hopefully you remember from the last video that W1 V1 plus W2 V2 is actually the dot product or the scalar product of V1 or V and W. So that is how we get our final result. So cosine of theta is equal to vector V dot vector W divided by the magnitude of V multiplied by the magnitude of W. And that is our final proof. So just quickly, if V dot W is equal to 0, then V and W are perpendicular or orthogonal. So you might start seeing that word pop up, but it means perpendicular. Also, the length of V dot W is equal to the magnitude of V times the magnitude of W. This means that vector V and vector W are actually parallel. All right, so a bit of a cool fact there. Then the last little note I want you guys to get down, we always use theta, all right, in our formula, even if we're given alpha. If we're given alpha, then we find theta using the 360 degrees in a revolution rule. All right, so find t such that 2, 3, and negative 2t are perpendicular. So jumping back up here, we can see that V dot W equals 0 means that they're perpendicular. So that is what we're going to do here. So 2 times negative 2 plus 3 times t is 0. Negative 4 plus 3t equals 0. Add 4 to both sides. 3t equals 4. Divide both sides by 3. Then we get our result, t equals 4/3. All right, that is the only example I've got here for you guys. Make sure you are following along closely. I know that proof was a bit full on, but the result we get is actually quite cool. So hopefully that clears up a few little questions you may have had about the angle between a vector. Now you can go ahead and use that formula as you please. We'll catch you guys in the next video.